Have you ever walked into a commercial building, maybe your office or a shop, maybe even a library, and just, felt it, that feeling? Maybe it's a bit too cold or oof, way too hot, and then you hear people talking about these crazy high energy bills. Yeah, it happens a lot. And often the reason is something we barely think about. It's literally right over our heads, the roof. So today we're doing a deep dive into something that sounds maybe a bit dry, but is actually super important: commercial roof insulation thickness. Now, I know insulation thickness really exciting, right? But honestly, stick with us. While it sounds technical, it's one of the biggest factors in how well a building works, how comfy it feels, and yeah, the bottom line. Our mission today: figure out why this thickness thing matters so much, what decides how thick it needs to be, and how knowing this stuff can help you make smarter choices about energy and keep buildings healthy long term. We're going to pull out the key bits, the important stuff to get you up to speed fast. Sound good? Let's jump in. Okay, so when we talk about commercial roof insulation, my first thought is like there must be one perfect number, right? But our sources are saying not really. For the common stuff like polyisocyanurate, polyiso, people usually call it, we're looking at maybe 1 inch up to like 4.5 inches. That seems like a pretty big range, doesn't it? It makes you wonder why so much difference, and how important is it to actually nail that number?
That's a really good point. And yeah, it gets right to the core of it. You're spot on. It's definitely not just one number. Choosing the right thickness, it's a balancing act. You're trying to hit two main targets. First, you need to meet your energy efficiency goals, whatever they are for that building. And second, the whole system has to follow the building codes and, fit the design plans. Actually, our sources point out something interesting: a 2.6-inch polyiso board. That's apparently a really popular choice.
2.6 inches. Huh. Popular. Why that specific thickness? Is it some kind of magic number?
Huh. Not exactly magic, but it's often considered a sweet spot.
A sweet spot. Okay.
Yeah.
Intrigued. Why is 2.6 inches the sweet spot? What's so balanced about that?
Right, think about it like this. Adding insulation isn't just about piling on more and more. It's finding that optimal point between how well it insulates its thermal performance and how much it costs. Sure, making it thicker does boost the R value, which, measures how well it resists heat flow. But for a lot of typical polyiso uses, once you go much past that 2.6-inch mark, the extra benefit starts to drop off, diminishing returns.
Yeah. Okay. So the extra cost for more material, maybe trickier installation, it starts to outweigh the tiny bit of extra energy savings.
Exactly. For loads of commercial projects, that 2.6-inch thickness is kind of where the cost curve and the performance curve meet really nicely. You get great thermal resistance without, spending more than you need to. It's the best bang for your buck, basically.
That makes a lot of sense. So 2.6-inch polyiso sounds like a good all-rounder. But I'm thinking about buildings with really specific needs. Maybe a massive data center that needs to stay cool, or a huge warehouse, or maybe something with a really complex roof design. That 1 to 4.5-inch range for polyiso still feels like it covers a lot of ground. Are there other types of insulation we should know about? What are they used for? It can't just be polyiso, right?
Absolutely. You've nailed it. There's
Yeah.
definitely a variety of materials, and that's key to understanding why thickness varies so much and where each fits in. So beyond those standard polyiso boards, which, like we said, are usually 1 to 4.5 inches and great for layering up to hit higher R values, we also have EPS and XPS foam insulation. That's expanded polystyrene and extruded polystyrene.
Right, EPS and XPS. Heard of those.
Yeah, they're these high-density, pretty rigid foam boards. You'll often see them in thicknesses from maybe 2 inches up to 6 inches. People like them because they're reliable. They give consistent performance for hitting energy targets. Plus, they handle compression well and resist moisture, which is good in certain spots.
Yeah.
But here's where it gets really interesting, maybe even a bit surprising. Tapered insulation systems.
Tapered. What does that mean?
Well, unlike a flat board, these are designed with a built-in slope. And get this, the total thickness can reach up to, wait for it, 40 inches.
40 inches. Seriously. Why on earth would you need insulation that thick? Is it even insulation at that point?
Huh. Well, it is insulation, but the main reason for that thickness is function. It's all about water. These systems are cleverly designed to create a slope on an otherwise flat roof. They basically shape the roof surface so water flows properly towards the drains.
Ah, so it's about drainage, preventing water from just sitting up there.
It's critical for managing rainwater, preventing ponding, the stuff that causes leaks and serious damage over time. So the insulation does double duty, keeps the building warm or cool, and manages water.
Clever. Okay, what else?
And then there's the greener end of things. Green roofs.
Oh, yeah, the ones with plants growing on them.
Precisely. These are more like mini ecosystems on top of the building. They combine insulation layers with soil, drainage layers, and actual vegetation. The whole buildup can be pretty substantial, anywhere from, say, 18 inches to maybe even 60 inches deep in total.
Wow, 60 inches.
Yeah, a lot of that is the soil and plants, obviously. But the insulation underneath is still doing its job, contributing to really good thermal performance. Plus, you get all those environmental bonuses, like reducing the heat island effect in cities, improving air quality. It's a really complex, multi-layered approach.
That's a great rundown of the options. So we know the what's,
Yeah.
but the big question is how. How do you actually choose? I mean, like you said, a roof in Miami is going to need something totally different than one in, say, Minneapolis, right?
Hmm.
Does the climate zone really dictate things that much? Or are other factors just as important?
You're thinking exactly right. How do you choose? And yeah, climate zone is huge. It's foundational. But it's definitely not the only thing. It's really a mix of several critical factors that all kind of come together to point towards the best insulation thickness for a specific project. There's no single magic formula, and each factor has real consequences for the building owner. Let's start with climate zone, because it's a big one. There's this thing called the International Energy Conservation Code, the IECC.
IECC, right, the energy code, people.
Yeah, pretty much the national standard for energy-efficient building. And the IECC definitely pushes for thicker insulation, higher R values, better heat resistance in colder places. Makes sense, right? Keep the heat in.
Makes total sense. Less heat escaping means lower heating bills.
Exactly. Now, flip that. If your building's in a warmer climate zone, you might be perfectly fine meeting your energy goals with thinner insulation. It can be more practical, more cost-effective, especially if you're doing a retrofit and adding loads of thickness is tricky or just not needed. So it's about tailoring it to the local weather.
Okay, so climate sets a baseline. But are there, like, hard and fast rules, laws you have to follow about insulation thickness? You can't just wing it, presumably?
Oh, absolutely not. Winging it is not recommended. That leads us straight to energy code compliance. The IECC doesn't just make suggestions. It sets actual minimum R value standards that commercial buildings have to meet, period. You'll see requirements like R25, R30, sometimes even higher, depending heavily on that climate zone again.
R25, R30.
Okay. And then, on top of the national code, your local building department often has its own specific guidelines. They might tweak the requirements based on local conditions, common building practices there, maybe even things like humidity levels.
So you've got the big IECC rules and then potentially stricter local rules, too.
Exactly. It's a layered approach to make sure buildings perform well in their specific environment.
Okay, you keep mentioning R value. We know higher is better, generally. But can you break that down a bit more? What is R value simply? And how does the actual material choice, like the Polyiso, versus that EPS foam effect hitting those R targets?
Sure thing. Material R value. Think of it simply as a score for how well something resists heat trying to pass through it. The R literally stands for resistance. So the bigger the R value number, the better that material is at insulating. Less heat gets through. Now, Polyiso, for example, is known for having really good thermal performance. It gives you about R5.7 per inch of thickness.
And R5.7 per inch.
That's right. So that popular 2.6-inch board we talked about,
Yeah.
multiply 2.6 by 5.7, and you get around R15, which is a decent starting point for many roofs.
Gotcha.
But, and this is important, different materials have different R values per inch. An inch of EPS foam won't give you the same R5.7 as Polyiso. It'll be lower.
So you'd need a thicker board of EPS to get the same total R value as a thinner board of Polyiso?
Precisely. So the material choice directly impacts how thick you need to go to hit that target R value required by the code.
Okay, that clicks. So it's not just the insulation itself in isolation, right? It has to work with everything else on the roof. You don't just, I don't know, glue the insulation down and call it a day. How does the whole roof assembly design, the deck underneath, the waterproof membrane on top, all that stuff, how does that play into deciding the insulation thickness?
You're absolutely right. It's a complete system. The roof assembly design is critical. Everything has to work together. The type of structural deck you have, the kind of roofing membrane you choose, whether you need vapor barriers. All these pieces influence how you can best incorporate the insulation for performance and, just as importantly, durability. And actually, something many people overlook is the coverboard.
Coverboard, what's that?
It's a thin, rigid board that often goes right on top of the insulation, just underneath the final roofing membrane.
Okay, why add another layer?
Several key reasons. First, it adds significant compressive strength. Think about people walking on the roof for maintenance, or heavy equipment being placed up there. The coverboard protects the insulation from getting crushed.
Makes sense. Insulation probably isn't designed to be walked on directly.
Not usually, no,
Well,
especially not repeatedly. The coverboard also provides a much better surface for the roofing membrane to stick to, which is vital for preventing leaks and wind uplift. And it adds just one more layer of protection for the insulation itself, shielding it from damage during installation or later on. It seems like a small thing, but it's really important for the roof's longevity.
I hadn't really thought about that, the coverboard protecting the insulation from foot traffic and impacts. Are there common problems if you skip it or use the wrong kind?
Oh, definitely. That's a great question. A really common mistake is seeing the coverboard as just an extra cost, something you can maybe skip to save money. But if you do that, or use one that isn't strong enough, you often end up with crushed insulation, especially where people walk a lot. And crushed insulation doesn't insulate very well, right? So your R value drops.
Right, you lose performance.
Exactly. Plus, the membrane on top is more likely to get punctured or damaged without that firm support. And if the membrane doesn't stick properly because the surface underneath isn't stable, you can get bubbles, or it might even peel off.
Yikes. Okay, so cutting corners on the coverboard sounds like a bad idea long term.
It really is. A bit more cost up front can save you massive headaches and repair bills down the road. Definitely not the place to skimp.
Good to know. So, considering all these parts, the deck, the insulation, the coverboard, the membrane, are there any other special jobs a roof might do that would need maybe even more insulation or a different setup?
Yes, the specific roof system function can definitely play a role. Think about roofs designed to actively manage stormwater, maybe holding on to rainwater for a while before releasing it slowly.
Like those blue roofs.
Exactly, like blue roofs. Or roofs designed for high solar reflectivity cool roofs to bounce sunlight back and reduce cooling costs. These specialized systems often work better with additional insulation layers. It helps the roof do its main job, manage water or reflect sun more effectively, while also ensuring the building stays energy efficient. It's about supporting that special function without sacrificing the thermal barrier.
This is incredibly detailed. Okay, so for our listeners out there who might be working on projects specifically in cold regions, I've got a pro tip pulled from our sources. For the best energy performance and to make absolutely sure you're meeting code in those really cold climates, think about using 8 to 12 inches of insulation. Often that means using layers of polyiso or maybe combining polyiso with other types in a hybrid system, just a practical takeaway for those specific situations.
Right, we've talked around R value quite a bit, and I feel like I get it, but can you really emphasize why it's so critical? How does getting a higher R value truly change how a roof behaves? It feels like more than just a number on a spec sheet.
It really is much more than just a number. It's the heart of the roof's thermal performance.
Let me restate it simply.
Yeah.
The higher the R value, the better the roof resists heat flow, period.
Right.
In practical terms, that means less of your expensive heated air escapes in the winter and less unwanted solar heat gets in during the summer.
Lower energy bills.
Directly lower energy bills. And hitting those R value targets set by the codes, like the IECC and local rules, isn't just about ticking a box for compliance. It's fundamentally about making the building more energy efficient overall. And remember, those required R values change depending on your climate zone. So picking insulation that delivers the right R value per inch for your specific location is absolutely key for getting good performance and efficiency that lasts. It's not just any number, it's the right number for the place. And actually, there's a key best practice here that our sources really emphasize, using 2 layers of insulation.
2 layers. Okay, obviously that adds up to more R value overall, but is there something else going on there? Some extra benefit beyond just doubling up?
Yes, absolutely. And it's a really important detail often missed in basic explanations. Using 2 layers does more than just increase the total R value. It significantly cuts down on something called thermal bridging.
Thermal bridging. Okay, what's that exactly? It sounds like heat taking a shortcut.
Yeah, that's a perfect way to put it. Think of it like this. In a single layer of insulation, you have joints between the boards, and you have metal fasteners going through the insulation to hold it down.
Right, screws and things.
Exactly. Heat can travel much more easily along those metal fasteners, or through tiny gaps at the joints. Those are thermal bridges shortcuts for heat to bypass the insulation. But when you use 2 layers, and you stagger the joints, meaning the joints in the top layer don't line up with the joints in the bottom layer.
Ah, like laying bricks. You don't put the gaps right on top of each other.
Precisely. Like laying bricks. You interrupt those direct pathways for heat. The fasteners might go through the top layer, but they hit solid insulation in the bottom layer below the joint. It breaks the bridge.
Okay, that makes a huge difference. I can see that.
It really does. It creates a much more continuous, effective thermal barrier. It's a simple technique, just staggering those joints, but it has a massive impact on the roof's overall real-world performance. It's widely recognized as a best practice in commercial roofing, especially when you're aiming for really high R-value systems.
That's a fantastic explanation. The staggered brick wall analogy really makes it clear. Okay, so pulling this all together, what does it mean for you listening right now? Why should you really care about polyiso thickness and R values and cover boards and staggered joints? We've covered a lot of technical ground. Let's bring it back to the real world benefits for someone who owns or manages a commercial building.
Right, this is the so what moment. And the so what is actually pretty significant. Getting the insulation thickness right delivers real, tangible benefits that affect your building every single day and its value long term. First off, like we've said, it directly helps your building meet its energy efficiency goals. And that's not just some abstract target. That translates immediately into lower HVAC costs. Your heating and cooling systems just don't have to work as hard or run as long when the roof isn't leaking energy. Think about your utility bills. Getting this right can make a noticeable dent. That's cash back in your pocket.
Lower bills are always good. What else?
Well, beyond the immediate savings, it contributes hugely to long-term roof performance. A properly insulated roof assembly tends to last longer because the materials aren't subjected to as much thermal stress, and you reduce risks associated with temperature fluctuations. It's also critical for meeting those IECC standards we talked about, and increasingly for things like LED certification. If sustainability and green building credit are important to you or your tenants, good insulation is non-negotiable.
Okay. Energy savings, longer life, meeting codes, green credentials, anything else.
Yes, and this is a big one often overlooked. Risk reduction. Proper insulation dramatically reduces the risk of condensation forming inside the roof assembly.
Condensation, like moisture getting trapped.
Exactly. Trapped moisture is bad news. It can lead to mold, rot, damage to the insulation itself, corrosion of metal components, and eventually membrane failure and leaks. These kinds of hidden moisture problems can be incredibly expensive to fix and can seriously shorten your roof's lifespan.
So good insulation is like preventative medicine for your roof.
That's a great way to put it. It helps prevent costly problems down the line. So really, thinking carefully about insulation thickness isn't just an extra detail. It's absolutely an essential part of any solid roof specification. And it's worth noting, this advice aligns with recommendations from all the major insulation manufacturers and respected industry standards groups like HSRE. It's tried and tested knowledge. Of course, for your specific project, always consult your local energy code folks and maybe a qualified building envelope consultant. They can give you the precise requirements tailored to your building and location.
Wow. Okay, what a journey. We started with a simple question about thickness, that 1 to 4.5 inches maybe, and we've gone through all these different materials, polyiso, EPS, tapered systems. We've looked at climate zones, energy codes, the critical role of R value, cover boards, even that clever trick with 2 layers. It's crystal clear now that picking the right commercial roof insulation thickness isn't just checking a box. It's a really strategic move. It impacts energy use, running costs, how long the roof lasts, even its environmental footprint. Making smart choices here really pays off, doesn't it? For your budget and for the planet, too. So, as we wrap up today's deep dive, here's something to think about. How many other parts of the buildings we use every day are like roof insulation? These unseen elements working behind the scenes. Things that quietly keep us comfortable, save us money, protect our investments, but we hardly ever notice them. What other critical systems, often overlooked, might be having just as big an impact on our lives and on sustainability? Something to ponder. Keep exploring. Keep asking questions. Thanks for joining us.